Hello everyone, this is the final lesson for the calculus part of the course. And now we've talked about taking derivatives with exponential functions. It's time to talk a little bit about solving problems with exponential models. Okay, so here's the first example. A culture of bacteria begins with 650 bacteria and doubles every 4 hours. What is the growth rate of the culture after 1 day? Okay. One quick note here, I have the slides pre-filled in, which will become apparent maybe why in example 2 because it's a bit longer. But yeah, I made it through a couple takes of the video and I kept messing up. So bear with me because I wanted to have it all written down first because there's some interesting stuff going on here. Okay. So first, here's our function. Okay, just to highlight what's going on here. Our initial population is 650. So that's where the 650 comes from. Okay, we're doubling. So that's the 2. Okay, and the reason we're dividing the exponent by 4 is because it doubles every 4 hours, right? So for example, if it's going to double twice, that would take 8 hours. If I plug in 8 for t, 8 divided by 4 is 2, and I have 2 squared, which represents the 2 doublings, okay? So with that in mind, okay, t is in hours here. T is the number of hours in the function. Okay, it wants to know what's the growth rate at a certain point in time. So that means I need to take my derivative. Okay. So this is a constant, so I can leave it alone, and then I have to do the derivative of this part over here. Okay, so just again to walk you through it, I left the constant alone. Okay. Derivative of an exponential function, so 2 to the power of something is 2 to the power of the same something times the ln of its base. Okay. Then I have to do the derivative of the inside, which is the exponent. So derivative of t over 4, that's a quarter t, so it's just 1/4. Okay. Now that I have that written out, okay, I wanted to know at the end of 1 day, so that's 24 hours. So I'm really just evaluating what's p of 24. So I plugged in 24 for t here. Okay, one thing I like to do with these is to tidy up the exponent, because if you try to run this through your calculator in one line, that's often where a little mistake will happen. So 24 divided by 4 is 6. Okay, so it's 2 to the power of 6, and that makes my life a little easier when I run this through my calculator. Okay, 2 to the 6 is 64, and when I run that through, I get 7,208.7 bacteria per hour, and that's my rate of change. Okay, so not too bad. Like other rate of change of problems, we just take our derivative and plug in the value and see what happens. Okay, I'm going to go over this with E as well. Okay, so just a reminder of how we make that change. Okay, right, my base was 2. I want it to be in terms of E, so I solve for the power, right? E to the power of what gives me 2. And when we work that around, we get ln of 2. Okay, so I replaced the 2 in my original function with e to the ln 2. Okay, so I combine my exponent, right? I multiplied these together, and I get t ln 2 over 4 is my exponent. Okay. Again, the reason we do this is because the derivative of e is a tiny bit simpler than an exponential derivative. So if I take my derivative, again, okay, I get to leave the 650 alone, okay, because it's a constant. Okay, e to the power of something, well, the derivative of e to the something is just itself, so I wrote that part down, then times the derivative of the inside. Okay, this is t times this constant, so the derivative of that is just that constant there. And now it's no different than the first time. Okay, I want to plug in 24, so I plug in 24 for t. Okay, I tidied up my exponent a little bit to make it easier to run through the calculator. So I have e to the power of 6 ln 2. Okay, but when I run it out through my calculator, I get the same value that I got before, 7,208.7 bacteria per hour. So in terms of, last assignment or quiz, okay, I don't have a preference. Okay, if you would rather work with the original function, that's fine. If you'd rather switch it to E, that's fine. Like I'm unless the question specifically asks. I won't force you to pick one or the other. But I know that down the road, if you do some more sciencey type stuff or calculus in university, you probably will get into the habit of changing it to E. So you might want to practice that a little bit there. Okay. Again, yeah, this is 6 ln 2. It's not 61n squared down there. Okay, here's the second one. This one is going to take a little while, so bear with me. This is the one where this is why I had to write it all down, because the first time I went through this, I got all the way to the bottom and then realized my calculator was in degrees, not radians, and thought, oh my goodness, I do not want to go through this all again. But again, some setup stuff. Diminishing height of a wave can be modeled by this equation. So you may have seen that towards the end of advanced functions when you did composite stuff. But the idea is this part here, okay, kind of controls your amplitude or the height of the wave. So this is an exponential function. The negative means it's going to be decreasing from left to right. So, right, e to the negative 0.5t looks something like that. Okay, if I draw its mirror image underneath, I get kind of a funnel here. And cosine is going to be bouncing back and forth between those two curves, right? Cosine, something like this. And that's how it's modeling a wave that's getting smaller and smaller. Okay. So determine the first time the maximum height of the water is less than 10 centimeters. Okay. So a couple things to note. Because it's talking about maximum height, that implies I should be looking at my derivative and finding the critical points. Less than 10 centimeters. Okay, right, I wasn't given a target time for this, okay, but this is a bit of a clue. I want my height to be less than 10 centimeters. So this part of my function controls the amplitude or the height. So that's what I've written down here. I want my amplitude to be less than 10 centimeters, which in terms of meters, right, my function is in meters, is 0.1 meters. Okay, so I started isolating to solve for t. So I divide by 0.25. Okay, take the ln of both sides. Okay. Okay, an interesting note here. Okay, when I go to clear this, dividing by a negative flips the inequality around. Okay, so I flipped my inequality, and I got t was greater than roughly 18.3. So that's saying that sometime after 18.3 seconds, that's when the first max will have occurred. Okay, but I don't know exactly when that is. I know it's after 18.3, but I don't know exactly what it is. So now we'll start looking at the exact part. Okay, so to find my critical points, I'm going to take the derivative of this. Okay, it's a messy function, okay, but we're going to put together the rules that we've learned to figure this out. So first thing to note, okay, again, that's a constant, so I can leave that alone and just focus on the rest. Okay, for the other parts, okay, I have two functions, right, an exponential and a trig function, so I'm going to use product rule in order to take that derivative. So the purple part is the derivative part. So I left my constant alone. Derivative of the first, okay, derivative of e to the something is itself, times the derivative of its exponent, like the inside. So derivative of negative 0.05t is just negative 0.05. Okay, times the second part. Okay, plus the first part times the derivative of the second part. So derivative of cosine is negative sine. Okay, derivative of the inside is 8 pi. Okay, in terms of tidying this up, okay, I have e to the power of something in both spots. Okay, so there's my slightly tidied up function. Okay, 0.25 e to the negative 0.05t, and then times this block in here. Okay, I'm looking for critical points, so I want to set this function equal to 0. Okay, well, we did this analysis the other day a little bit. Okay, the exponential function part can't be equal to 0, so I don't have to worry about this. Okay, it's this block. Okay, this could potentially have roots? Probably will, because they're trig functions. So I have to set this equal to 0 to find my critical points. Okay, this has a mixture of sine and cosine. Right? How am I going to do that? Okay. One way would be to attempt using one of the double angle formulas. Right? I could rewrite cos 8 pi t as like 1 minus something, but it would get really messy. Okay, so we're not going to do that. Okay, so what I'm going to do, I brought this term to the left-hand side. Okay, and then I divided both sides by cos and both sides by negative 8 pi. So I get this expression right here. Okay, and this is handy because now I have sine over cos of the same argument. So that becomes tan. Okay, and when I divide these out, I get negative 0.00199 roughly. Okay, so now I take my tan inverse. So two things to talk about here. Okay, tan inverse of this number, so I'll change color here. Tan inverse of this number is this part here. Okay, the plus pi k, okay, where that's coming from is if you have your tan function, okay, which looks something like this, the period of tan is pi. Okay, so that's why I have plus pi k. So this is my root plus multiples of pi. Divide both sides by 8 pi, and I get this. Okay, so now I have a little expression that generates times. Okay, I want to know the first time after 18.3 where this occurs. So now I would like this to be greater than 18.3. Okay, so I use that to solve for k. So I brought this piece over, divided it out, or sorry, multiplied by 8. So k has to be bigger than 146.4. Okay, k has to be a whole number. Okay, it's whole number multiples. So it could be that k is 147. Actually, I think I wrote that down below. Let me see. Yeah, okay. K could be 147. Okay, but you know, we're somewhere way down the road with my trig function. Okay, it could be a max or it could be a min. So if 147 is not the max, then 148 will be the max because they alternate back and forth. So it could be this is when k equals 147 or 148. Okay, so from here, I'm taking kind of the, I don't want to say the cheating route, the shortcut. You know, I could try to take my second derivative and do the test, but my derivative is messy enough. Okay, I don't want to make this any worse. So I'm just going to go back into my original function and see which one of these is a max and which one is a min. So I started with 147. So I put this back in for k and got this is my value of t. Okay. I plugged t back into my original function and got negative 0.09975, which at first bothered me, but then I remembered this is in meters. So this is negative, 9 centimeters, 9.9 centimeters. So it's okay, but it's negative. So this is a local minimum. That's not what I wanted. I wanted the peak of the wave. So then I ran the same process with 148. Okay, I got my time. Okay, and I plugged it into my original function and I got positive 9.93. So after all of that, okay, in conclusion, at about, realistically, it's pretty much 18.5. So at 18.5 seconds, that is the first time the peak of the wave is less than 10 centimeters. Okay, there's a lot of stuff going on there, but it brings together a lot of the different ideas from the course into one question. Okay, so again, that was our last video. So thank you for watching. Okay, especially thank you if you've put up with all these videos all the way through and watched them all. All right, and of course, if you have any questions about the practice work, which should be over here, okay, then feel free to send me questions about that. All right, thank you.